we will be talking about 5 with bit error rate performance channel. the week 5 was basically on bit error rate, performance and fading channels. And the outline will be quick review of AWG and BER, which is basically from lecture 1 to 19, which was essentials. And then coherent detection, models and BER derivatives like BPSK, and differential detection, which is we will talk about the principle DBPSK and what is the bit error rate about that. Then fading channel model, flat fading, instantaneous SNR, and relay fading, which is having PDF, average BER, derivation. Then moment generating function method and its applications, finding the comparison, which is coherent versus different fading and diversity. So there are some review that which I like to tell you what our AWG and BER basics. Like we are having a signal model, which is a coherent baseband, coherent in the sense that whenever we do that modulation, so this is oscilloscope or oscillator, we call it. So there are two types of oscillator, which is coherent and non-coherent. Coherent if the phase cos 2 pi SCT plus phi. If the phi is 0 and if the input is AM cos 2 pi FMT, where FC is very, very greater than FM. And in that case, when we are having this phi as 0, then it is the coherent. Okay. And in that case, the received signal T is equals to SI of T plus NT if it is AWG in mass. And so if we call it energy per symbol, which is ES, with energy EV and instantaneous SNR, then instantaneous SNR gamma is equals to ES by N naught, where energy per symbol is there, which is different from EV. So in case of BPSK, since we are having N is equals to 2, so ES is equals to 2, right? So in this case, BER, which is the probability of bit error rate, is equals to Q over 2 gamma, where 2 gamma is SNR, is equals to this. And we talk about the state probability, where if it is greater than particular value, that is Q of X, so it is greater than here, then it is integration from lower gamma uh, to infinity from here to here. And 1 upon root over 2 pi sigma square, where sigma is equals to 1 because this is a log normal distribution. E power minus t square by 2. The important identity used later. This. Okay. So if you talk about the
అందరూ యూజ్ చేస్తున్నారు కానీ 10% పీపుల్ మాత్రమే గూగుల్ ని స్మార్ట్ గా యూజ్ చేస్తున్నారు. బట్ డోంట్ వరీ, ఆ స్మార్ట్ పీపుల్ యూజ్ చేసే ట్రిక్స్ నేను మీకు షేర్ చేయబోతున్నా. అండ్ థర్డ్ ట్రిక్ ఇస్ ద బెస్ట్. సో ట్రిక్ నెంబర్ 1, ఒకవేళ మీకు ఏదైనా టాపిక్ కి రిలేటెడ్ గా ఉన్న అన్ని ఫ్రీ కోర్సెస్ ని తెలుసుకోవాలి అంటే గూగుల్ సర్చ్ బార్ లో ఆ స్కిల్ ఆర్ ఆ కోర్స్ నేమ్ ని ఎంటర్ చేసి యాడ్ చేయండి colondrive.google.com. ఇలా సర్చ్ చేయండి, ఆ టాపిక్ యొక్క అన్ని ఫ్రీ కోర్సెస్ లింక్స్ మీకు దొరుకుతాయి. ట్రిక్ నెంబర్ 2, ఒక
coherent detection design signal model, we are having SOT binary model. SOT is equals to ES cos omega naught T. S1 T is minus root of. This is simple BPSK where you're having simple S plus 1 here and plus minus 1, S0 and S1. Which is a function of time. The receiver, we are having a match filter, which is a correlator with perfectly known carrier phase and a channel gain H is present. So coherent decision statistics, like Y is equals to what? the receiver of receive signal RT and then phi t, then it is equals to root h root over ES plus n, where n, this is small n is a white Gaussian noise, and we're having zero mean, and the sigma is equals to n naught by 2. Hi, Sarla. Anything? So we are having this mass filter. The mass filter aim is to reduce the noise and maximize the SNR. In that case, this is a B gap goes to 0 if y greater than 0, or else it is 1. So sometimes we call it as a 0, 1, or sometimes it is plus 1 and minus. So it varies. Basically, based on one decision, you are deciding one symbol, and other decision, you are deciding another symbol. That is the aim. The coherent BPSK, which is BER in AWJ, we will just derive it. So it is a conditional on SNR gamma. PB of gamma is equals to Q root over gamma. So using the Q function, we can just solve it because this formula was there here. Can use it here directly, and this form is very useful when averaging over random gamma. Why random gamma is there? Since this is uh, the random variable, so you cannot directly use this normally. So you have to use the expected value of Q of, because this gamma is a random variable. Now we talk about this coherent MPSK or the QPSK, which is having a symbol bit error. So coherent MPSK symbol, which is the error probability, is equals to 1 upon pi, some integration from 0 to m minus 1 pi by m, exponential of minus gamma sine square pi by m divided by sine square theta d theta. For QPSK, what it equals to, it will be equivalent to 2 orthogonal PPSK, which is very, very similar to PB of gamma equals to 2 gamma. General approach is nothing but expressing the conditional error as an integral of exponential of minus a gamma by sine square theta and average over PD. So we are also having differential detection, a principle. So differential detection, which is non-coherent idea, is like encoding the information is difference between successor symbols, no explicit base reference required. This DPPSK symbol mapping. And here we're having, see, the theta k of time k is depending on previous symbol, theta k minus 1, plus one of the BPSK moderator symbol, which is 0 or 1. So this, it is differentiated or the by the pi. So it is basically uh, 1 theta k. And then put it k. The receiver compares the successive receive symbol based on this. If we just multiply with k minus 1, k minus 1, so it is equals to in the magnitude of x square e is e power j delta theta k plus. Decision uses a sign of this one based on this. Now in DPSK differential binary shift key, BR in AWG, SNR instantaneous. In AWG, which is having no fading, instantaneous BR for DPSK by 2 exponential minus gamma. Then gamma is equals to the exponential dB penalty versus SK at high SNR in DA, where the remark is coherent BPSK, which is equals to root over 2 gamma is 1 by 2 exponential of minus gamma for large gamma, but exact form different. Now if we talk about coherent versus differential comparison, the exact forms, the PB of coherent of gamma is of root of where PB of differential of gamma is equals to 1 by 3 power minus gamma. So directly it is exponentially decaying with respect to gamma. So this in this case of coherent, where it is differential. Asymptotically, we can say that it is also in directly proportional e power minus gamma, but it is scaled by 1 upon root over 4 pi gamma. So this differential detection incurs a penalty which is approximately 3D lack of phase and longer errors. Obviously, when we are having this pi, the differential, so you are having this penalty of and 1 by 2 in dV is equal to 3. That's why it is. Now we talk about some fading channel. So we are having a flat fading model. The baseband flat fading model, which is R is equals to simple. Now, if the fading is not there, then simply R is equals to S plus M. If the fading is there, the H is there. So where H is a complex fading gain, which is random in nature, and N is complex uh, Gaussian with respect to 0 and N0. Sometimes it is complex, sometimes it's real. You can just ignore that. Instantaneous SNR will definitely be equals to mod of H square into ES. ES is the energy of S divided by N0. Okay. So the key idea is the BER given gamma as in AWZ average over PDF of gamma, which is equals to PP or equals to 0 of gamma, F of gamma gamma d gamma. So this averaging produces significantly different performance than AWZ. I will tell you one very good so as we know, we are having voice signal from 300 hertz to 3.5 kilohertz. The audio is 30 hertz to 20 kilohertz. And in audio, the voice is there. And in video, we are having 0 to 4 megahertz, where FM 88 megahertz to 108 megahertz. We're having 100 channels, where one channel equals to zero point 0.2 megahertz or 200 kilohertz. So similarly, AM is amplitude modulation. FM is frequency modulation. The baseband signal frequency is very less. When we modulate it, it, it changes. Right. So in amplitude modulation, you are having 550 kilohertz to 16, where 110 channels are there, where one channel. Okay. So this is all about the signal frequency, which I have wanted to tell you. But if you talk about as the course started itself with the 2G, 5G, so what I want to tell is in MIMO, we are having end transmit antennas and then receive antennas, where the MIMO system can be systematically represented as having parallel channels. So here we are sending different messages to different antennas. So thereby increasing the spatial multiplexing, where we are having different channels. But if you talk about OFDM, OFDM is orthogonal frequency division multiplexing, where wideband channel into n narrowband channels are divided. I'll come to that derivation of the bit array. In this lecture, Aditya sir taught very well. So wideband channel into n parallel narrowband channels. So where we are having data is converted to serial to parallel. Once it is converted into serial to parallel, it's the endpoint IFT. Then again, parallel to serial multiplexing is there. When we add it to cyclic prefix, we will be getting the baseband output. When the baseband output is there, the cyclic prefix will be removed. Then serial to parallel. Again, it is passed through endpoint FFT. And finally, the coherent detection. Here, the coherent detection is there. Because once the coherent detection is not there, we cannot directly detect the signal. And we will be getting the baseband symbols. Okay. So in CDMA, MIMO, and OFDM, the basics of 3G wireless communication. So since in desktop in the receive signal, yt is equal to summation of I is equals to L minus 1, AI st minus tau I, e power minus j 2 pi f c tau I. So this is this complex spaceband receive signal. So when we are having narrowband signal, in that case, we can assume this st minus tau I is equivalent to st. In when this FM is very very less than FC, that is example of GSM, where FM is 200 kilohertz, was 900 megahertz. In that case, we can directly uh, assume this FM is less than FC, and this is complex receive baseband signal without modulation, because this tau i's are there with respect to multipath fading. Okay, so this when we convert this, that can become out. So here, if we write the yi, so this h, which is a complex fading channel, is equal to summation of I is equals to L minus 1, where L taps are there, because in channel also we are having L taps. AI e power minus j 2 pi fc tau I. So it depends on the attenuation delay of the different multipath component, which is AI and the tau I. So suppose we are having L is equals to 2. So in that case, H is what? Uh, and A0, A1 is equals to 1, where we can keep A0 as A1 is equals to 1, which is leading to destructive fading. The coefficients of H varies depending on the various channel attenuation factor AI and tau I. And these are the fading coefficients. Got it, but so we saw the basic equation for the fading coefficient, which is they basically depending on the attenuation factor and the delay. But the diversity, if we talk about, so it can be employed to overcome fading, to overcome the effect of defading, because as we know, defading is there. So the principle of diversity, do you think what is the difference between diversity and MIMO? That difference, diversity and MIMO. So if a single link is in defade, so performance will be very bad, and we saw that bit error rate will be directly proportional to defade. So in case transmitter having only one link, there will be no alternative. Okay. Single link between transmitter and receiver. If this single link is defamed, it will disrupt the communication. So consider a system with multiple links. So this is the principle of diversity. So multiple links between transmitter and receiver. But in antenna case, which is multiple antenna at the transmit and receive is different. In that case, you are having different antennas. You are also creating the link, but you are sending the different messages. Whereas here, you are sending the same messages to different links. So that whenever one link, if it is in a D phase, other link will work. And in that case, the information can be easily transmitted. Okay. So there will be two paths. So therefore, the communication is not restricted. So example of diversity is like we are having receive diversities. Introduces the diversity, multiple receive antennas, multiple transmit antennas. Okay. So suppose we are having T1, transmit 1, Y1, Y2, X, Y1, Y2. So H1 is equals to fading coefficient between T1 and R1. 2 is equals to fading coefficient between T2 and R1. Symbol receive on R1, symbol receive on R2. So if we system model is y1 is equals to h1x plus n1, y2 is equals to h2x plus n2. Noise at receive 1 and receive, where n1 and n2 are the Gaussian and zero mean. So simply the expectation of this is zero and the cross correlation is also uncorrelated. Now, if we write y1, y2 is equals to h1, h2x plus n1, n2, then we can have y is equals to h bar x plus n bar, where we combine y gap is equals to w1 y1 plus w2 y2. And here, since you want what you want, you at the receive y. So y should be y at the terms of y. We want to maximize this w. Okay. W1 y1 plus w2 y2. So this w transpose y is equals to w transpose hx plus n, where w transpose h x plus w transpose y, and SNR is equals to mod of W transpose H square into P, which is the transmit power of X symbol, divided by expectation of uh, W transpose N square. Now you may wonder why we have directly taken the mod of square of these, because what happens, H is random, H is normal random. Okay. Whereas this is the random variable W transpose into N. That's why you are taking this expected value, where here you are taking directly the mod. So SNR is this, and we want to maximize this SNR. Now expected value of this sigma square mod of W square. W1 square sigma square plus W2 square sigma square. If the W1 number is same, then it is mod. Otherwise, sigma square is common, and then you are keeping it up. Sigma square mod of W square. I'm keeping E of N. Again, and again we are distributing it. And if it is same, mod of H1 H2 is nothing but, if it is a dot product, that's cos theta, W square will be going. So it is equals to P of sigma square mod of H square cos square theta. And theta is what? Theta is the angle between W and H. W was the weighing factor. W y is equals to W transpose y bar is equals to W transpose W trans right. W trans right. Our aim maximize and in order to maximize the angle between the weighting factor, coming factor, and h should be zero because cos theta has to be, or it should be opposite 180 degree because it is cos square theta. Cos 0 is 1 and cos 180 degree is minus 1. So if you square it, it will. So for SNR to be maximum, theta should be 0 and W has to be along H. W should be proportional to H. This maximum combine. In order to combine properly when we are having the two receivers at the same time and we're having one transmitter. So very good logic. And in that case, the W has to be directly proportional to H. The weighting factors should be equals to H1, H2 divided by into 1 by mod of H. The complex coefficients. Finding at receiver, if we combine W is equals to H divided mod of H, then in that case it is maximize the SNR at the receiver multiple answers. Example, we asking H1 H2 again. Y1 is equals to H1x plus N1, Y2 is equals to H2x plus N2. Now, it is also given E of mod of N1 square is equals to E of mod of is equals to sigma square, which is equal to N Y1 Y2 is H1 H2x plus N1 N2. So optimal MRC receiver, which is vector, combining receiver, combining vector. It is combining vector. W is MRC ratio combine. H is equal maximum ratio R is equal. You can also calculate that. That was we are having multiple noise power on entire and pi is equals to hx E of n pi is equals to sigma. And maximum ratio combining is square of h square p divided by p divided by sigma optimum receiver combined optimal receiver combined maximum ratio antenna BER of multiple wireless system Z is equals to R plus H plus where H1 H3 is then identically distributed or this H which talking about mostly are the Rayleigh framing channel coefficient where expected value of HI square is equals to in that case in that case the the G is equals to chi square random variable but because once we are having when we sum uh, individual Rayleigh framing distributed signal and square it and sum it, then chi square random variable degree of freedom. And in that case, this is the distribution that chi. This receive SNR in that case G of sigma is directly proportional to B. Previous SNR and NR B we're having multiple antennas. Talking about two, then we have multiple antennas. Case as we know the BER is equals to of root over S. The is it it having multiple antennas is the random the average with respect to G to derive the average B. But the since G is random average B and have that case the exact expression of multiple BER of multiple antenna divided by 2 where lambda is equals to SNR of and of at high SNR basically 1 by 2 by SNR. So at high SNR the BER is equal to L minus L 1 divided by 2 SNR or L is equals to calculate. So this the SN the BER is approximately inversely proportional to SNR power of 2. The high SNR approximation for L by 2. Diversity is actually used in several 3G, 4G, WC. VAR is decreases with respect to of receive L antennas. This power of receiver is equals to this. VAR is must be SNR. What is the reason behind our relay? Because now the things comes in a picture. A deep fake analysis on antenna system I is equals to HX plus N. Diamond by H1 N. And after match this as we so this the receiver when we are having the deep 20 emission exactly when we then P of P is very less than sigma square when the noise increase right in that case uh D is less than 1 sigma square by P or 1 by SLR so for deep fade so um then the probability of deep fade how will you find so probability of deep fade when G is less than 1 by SLR now we keep this 0 to SLR and the probability it is equals to 1 by L minus 1 by L by L. Probability of deep fade is that is inversely proportional to SNR of with increased number of antennas L. Probability of deep fade this leads to significant decrease in DER is directly proportional to probability of deep. We are having a transmitter and we are having the receiver. The deep fade happens, it is directly proportional to 1 by. So if they are having L links, where EI denotes the event that I is in D. Let's say the probability of having link I in D is equals to probability of link, all the link fade will be SNR. For system to be in deep fade, all links have to be in deep fade. So that will be some directly in this section of all the events happening at the same time. Probability of the events happening in PR of E into PR of EI. PR of EI is equal to and SNR power L. Probability of deep fade is equals to 1 by SNR power L. This is L independently finding fading channel between transmit and receive. Multiple antennas distributed in space is known as spatial diversity. One key assumption in all HL are independently for this to hold antennas has to be very significantly apart. Now all the antennas are independently fading. What if they are also a joint probability distribution when all these antennas are in deep fade? So they have to keep how far they can be jointly fading also. So, but for that independently fading, we are keeping antennas in a particular distance where D denotes the spacing between antennas. So antennas are uniformly spaced with distance. For independent fading, by 2 which separation or wavelength of the carrier. Because the velocity of light and FC, example, the by 2. Consider 3D 4D How to characterize diversity of a system? Diversity order. Diversity order is the but yeah, again, diversity order of system antennas is probability of error. SNR is equals to having deep fade, it is H, right? And that's what I will 1/2. How does the wireless channel affect the wireless number? As we know, HT is equals to AI delta T, I is equals to part component. Here L is different part component here, and whereas in the channel responses, power profile, as we know, I is equals to part of AI square AI, and is equals to LGI is equals to gain of the T minus tau. And this is simple AI if it is simple and power gain power supply when we are having trying to find the target gain of fire from 0 to 3, right? Delta T minus again delay is tau. So if talked about it is multipath power profile is having various delays are spread over interval of. So how to characterize the delay spread? When we are having the first arriving come tau 0, last arriving come tau L minus tau T max is tau L minus tau 0. Maximum is power. Large number of paths with nice flow So instead of maximum average delay is equals to D naught T tau 0 plus n tau 1 summation of DL minus weight each delay tau I by fraction of power BI of I power. I think the maximum delay से RMS delay squared. Another important parameter of wireless communication bandwidth. So another important parameter of wireless communication. So we are having XT and YT. So we know YT is equals to XT convolution with HT. So receive signal is equals to transmit signal and the response. Whereas in frequency domain, XF YF is equals to XF into HF, the frequency response of the received signal. Then when we are having this HF, which is BC, the coherence bandwidth, when BS is less than BC, then it will be no distortion. It is called flat fading because here the signal will easily pass through this. Okay. The bandwidth of the flat portion of the channel is called frequency response. When we are having BS less than BS, which is greater than equals to the coherence bandwidth of the channel, and we are having the frequency selective fading. So the flat portion of channel of the bandwidth, the flat fading, no distortion, whereas it is will be frequency distortion. So HT, as we know, AI delta T minus tau I. Summation I is equals to 0 to L minus 1. The delta T minus tau I minus infinity to infinity delta T minus tau I e power minus j 2 pi ft dt. It is equals to e power minus 2 pi f tau I. And when we convert into frequency domain, so delta T minus tau I is directly leading to e power minus j 2 pi f tau I. So the Fourier transform of HT, the Fourier transform of the channel is nothing but AI e power minus j 2 pi f tau I. So at f is equals to 0, the phase equals to 0, where f is equals to 1 tau I, 2 tau I, phase equals to pi. Phase has changed significantly, the frequency response has changed significantly. So see, you can see that f is equals to 1 upon 2 tau I. In that case, and bandwidth is equals to 2 into pi tau I. So in that case, bandwidth, when the bandwidth is equals to 1 upon tau I, that case the phase has changed significantly. In general approximation, the bandwidth of the coherence channel is 1 upon tau I, sigma tau. Coherence bandwidth is equal to delay spread. So tau I, and f is equals to 1 upon tau I. That case phase will be I, which is significant chain, and this is equals to coherence bandwidth equals to typically just 2 microseconds. So when uh, the sigma, this one frequency selective fading, when it is greater than less than 2 microseconds. All about ISI, you know. The ISI is a time domain analogous of frequency selective fading, which is in frequency domain. Now, this Doppler is very beautiful concept. Like when we are having a base station and mobile is moving, it leads to change in the frequency of the wireless signal received at the mobile. So this is equals to Doppler effect. The change in the frequency of the received signal due to motion between transmitter and receiver is Doppler effect. So when we are having the base station here, and mobile is moving in the direction. So Doppler is maximum when theta is equals to 0 or 180 degrees. So with angle of theta with respect to base station, velocity is v. Very common question asked. So v, the Doppler shift will be v cos theta by c. And why it is v cos theta by c into fc? Doppler frequency derivation. Why? Because if we have the receives frequency, if fr is equals to the carrier frequency at the receiver, the change in the received signal frequency due to motion between transmitter and receiver is the Doppler frequency. So we are having received signal frequency fc, fr is equals to fc plus fd. Okay, some change in there. So carrier frequency, this is v cos theta by c into fc. So when we are having theta from 0 to pi by 2, then cos theta is greater than 0. Therefore, this cos theta greater than or equal to 0. If this called receive frequency is greater than carrier frequency, mobile is moving towards base station. And we are having less values. Mobile is moving away from the base. Example, the if the relative speed is v, and the angle between velocity vector, then transmitter sends they transmit the receiver is instantaneous range RT, let's say. The propagation delay is delta T is equals to RT by the signal is nothing but T is equals to by CT T minus tau L, tau T. This equals to cos 2 pi FCT by FC RT by T. Instantaneous frequency FD by FC is nothing but impact of Doppler on wireless channel. While is moving. Therefore, delay is changing. Tau I is equal to tau I minus cos T by C. Here the depth actual derivation is there. What is happening is like when we are having this distance between mobile and a base station is decreasing. Therefore, delay tau I is changing. Tau I of t is equal to tau I minus cos theta t by. Therefore, tau I t is equal to tau I minus t by c. This we replace this here tau I by after we put because delta is actually weird. Hence, the speed this part is considered S is there. Time is equal to distance by first time. Doppler is giving time selective. Frequency selective fading is different. Time selective fading is time of the time of the channel. Time varying channel is also known as time selective by C. C is equals to is equals to pi by 2. Channel has changed is equals to 1 of Derive the BER for coherent BPSK data. To state the signal model BPSK at the exact bit and probability expression P of gamma in terms of function and where gamma is equals to EV by N. Basically, we will be going through real baseband signal where S is having plus over EV and N is actually Gaussian zero mean. So this is when rule is nothing of error. Then it is positive. Probability of received signal is less than 0 of N less minus EV. Analyze the Gaussian. PB of gamma is equal to P of Z less than or minus EV by sigma n, where sigma n is equal to root by non big. Finally, when we are deriving it, the BPSK, it is equals to PB of gamma. There was Q of root over. And proving the Q function integral identity. Prove the identity which is a Gray's form, Big's form. Q of x is equal to pi integration of from 0 to pi by 2 minus x square divided by 2 sine square theta d theta. Okay, starting from the standard definition. Now we do get it. Other steps. And we are having the Q function, Q of x, where it ranges from tail probability x to infinity, e of minus t by 2. Then using the identity, 1 by t is equals to pi 0 of minus theta, or perform the substitution t is equals to x divided by sine theta. Method of contour variable transform classical derivation. This derivation uses derivation from x e power t square by 2 dt by 2 integration of x by sine t power t theta. The q of x is equals to this integration in the order and evaluating the leads to stated identity. DPPSK, BR, and AW. Derive the bit error probability for differential PSK with no fading. Show the close. DPPSK binary phase shifting compares two symbols assuming wide Gaussian. The condition error probability for dB of A. Brief justification is the decision after the part such that the probability 1 by dB of DPPS. This exhibits approximate average score in PSKB even the daily and the average B for coherent. So PB 0 to 2 of I it is like this is also the case of random approximate using Craig's form for PB 0 to 5. Keep on solve it here. dB is equal to 0 to pi. Average dB, the average can close to 1. That to that on is come. The numerical comparison TSK average B, EBP average B, computing and calculate the doctor taking the selection.